Good morning, and welcome to today's electronic design webcast. Our topic today is UL/IEC 62368-1, got you down, IsoMOV to the rescue, sponsored by Bourns. I'm James Moore with Endeavor's Design and Engineering Group. To start, let me explain how you can participate in today's presentation. First off, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box, and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We will answer as many as possible during the Q&A session following the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click the Send button. If you'd like a copy of the presentation, please click on the event resources on the side of your screen to download the presentation. Also, please be aware that today's session is being recorded and will be available on Electronic Design's website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speakers. Paul Smith is a field application engineer at Bourns, responsible for helping designers with circuit protection solutions. He has more than 40 years of engineering experience and holds over 20 patents. Thomas Tran is the technical marketing manager for the Circuit Protection Division at Bourns. Tran has more than 20 years of experience in circuit protection manufacturing, equipment design, and application development. Now let me turn things over to our presenters. Gentlemen, the floor is yours.
Thank you very much, James. Welcome, everybody. Before I talk about IEC 62368-1, I want to go over some issues involved with dealing with that. And if you take a step back, some of this might be obvious, but if you look at the trends of what's going on, everything's getting smaller, geometries are getting smaller, distances are getting smaller. Therefore, they're becoming more sensitive to voltage, right? You got electric field breakdown, volts per meter, the meters are getting smaller, so the volts are getting smaller. So things have to fit in a smaller board space. And to address the issue of protection from overvoltage, GDTs and MOVs are often used. These are kind of the basic components. They've been around for a long time, but they really give you the best protection per area that you can find. There are other technologies, TVS diodes come to mind. But for the same level of protection, TVS diodes are actually bigger parts than some of these older technologies. GDTs and MOVs are often used together because each one has a disadvantage, and I'll be discussing those later. But when you combine them, each device overcomes the disadvantages of the other. But putting two devices on a board makes it bigger than you would want. You can see some pictures there on the right, GDT and MOV. And what we're going to be talking about today is a device that will collapse that down into the size of that single MOV. Now, I use the word MOV, and some of you have already tuned me out because you have experience with MOVs. You've been burned by them, both metaphorically as well as perhaps physically. Because one of the end-of-life phenomena that MOVs can go through is a fairly violent and impressive burst into flame. Not many do it. It's a certain percentage out there, which is small, does occur, and it's billions of these devices are on the field, so 1% of a billion is still a lot of little small fires to deal with. So if you don't like MOVs because of that, you'll like what we're talking about today. Now, the IEC 62368-1 spec, they do recognize this issue with MOVs, and so they've listed a few options on how to deal with this. The basic failure mechanism is overheating due to too much current going through the MOV. So one way you can solve this problem is to put a fuse in series with the MOV. When the current gets too high, the fuse blows, removing the current, so the power dissipation goes to zero, the MOV doesn't heat up. Alternatively, you can use a thermally activated fuse. So the current starts increasing, the MOV starts heating up. Before it reaches its flash point, the thermal fuse will engage, open removing the current, and the MOV cools back down. Or number 3, just embrace the fact that it's going to burst into flames, or maybe burst into flames, and so just keep it away from other combustible material. Or number 4, put this in a fire enclosure. There are some exemptions, though, for MOVs that have a substantially higher trigger voltage or clamping voltage than the normal standby current. The typical failure mechanism for an MOV is leakage over time. If there's always a voltage across the MOV, either DC or AC, the leakage current goes up over time. I'm talking years. And leakage current goes up, there's a voltage across it, that's power dissipation, which makes it get hot, which makes leakage go up even more, which makes it get even hotter. So, right, you got this thermal runaway mode. But if you can put that clamping voltage very high, even though there's a voltage across the device, the leakage becomes very, very small. One way to do that is to put a GDT in series, and you can see that on the circuit diagram here. I have a AC line voltage, and I show 2 GDTs in series with 2 MOVs, and that has been around for a long time. That's a very common configuration that's been around for decades before my time. What's going on there is the GDT is a gap. It's a gas discharge tube. It's like a little neon bulb. Voltage gets high enough, it'll trigger and become conductive. But until that time, it's an open circuit. It's a gap. There is no leakage. So that solves the leakage aging problem for MOVs. What I show here is for for common mode surges, right? The surge occurs on both of the outside conductors. Has to get quite large before this thing triggers. And I show a 3 kV GDT, 300 volt MOV, so 3.3 kV volts is required to turn on that string. I also show on the right a protection for a common differential mode surge, right? The surge occurs across the 2 outside terminals. And that's a strange looking symbol there, and that's what I'm going to be talking about today. It's an IsoMOV or a GMOV device. So what is this IsoMOV? It's called a hybrid protector because it contains components of both the GDT and an MOV in it. We've taken our flat GDT technology, right? A normal GDT is about the size of the last index of your little finger, and we're able to squish that down, be very thin, and we use the technology that we've learned from doing that in designing this MOV. You can see I've got 2 MOV discs on the top and bottom with the GDT stuck in the middle. And it looks just like an MOV. You can take an existing MOV out of your circuit and plop this guy down and immediately get an improvement, right? There's no redesign of the PC board or anything. On the right-hand side, you can see some schematic symbols. You can see the 2 MOVs on the top and bottom with the GDT in the middle. That's a series circuit. So 2 MOVs in series is what? It's just another MOV. So this is equivalent to that series combination of MOV and GDT that I showed you earlier. And then we've suggested a symbol there on the right-hand side that kind of shows the MOVs on the end and the GDT in the middle. And that's what that symbol represents. It's that IsoMOV product. And here's a blow-up of what's going on. There's metallized contacts on the top and bottom, similar to a normal MOV. But in between the MOVs is a evacuated space where the GDT gases are. They're sealed with glass on the circumference. And that yellow area inside is the electrodes for the GDT. That's the active GDT area. That's where the arcing and the firing of the gas occurs. On the right-hand side is a close-up of the glass seal that you can see there. So how does this thing work? What I show in the upper right-hand corner is an AC waveform, and we've superimposed a surge on top. That's a 2 kV surge on top of a 60-cycle waveform. And it clamps just like a normal MOV. You can see that on the bottom, that 2 kV is dropped down to roughly 700 volts or so. Now, because the IsoMOV has a GDT in it, you will get a little increased spark over voltage, a little spike at the front end before it enters this clamp mode. And I'll show you some details in a minute. But after the surge goes away, the MOV returns to an open circuit like normal, and it just goes on. So if I blow up that waveform and I zoom in on that clamping voltage, you'll see the surge in yellow. That's a 2 kV surge. And the white is the IsoMOV clamping voltage. You can see that broad area is around 700 volts. That's the MOV clamping. And that front end, that spike goes up to about 1.5 kV. That's how much voltage it takes to spark that GDT. And you're looking at that, and you're saying, oh my gosh, that's not much different than the 2 kV voltage that my surge is. My circuit is going to see that white voltage. I'm still going to see 1.5 kV. Gosh, that doesn't sound very good to me at all. So I need to remind you that that spike is very narrow. For example, your equipment is assuredly protected against ESD, right? That's 8 kV, but it's very, very short. There's not much energy in there. Well, this is 1.5 kV, and it's probably a few 100 nanoseconds wide. There's really not much energy in that pulse. There's a lot more energy in that lower, longer pulse. So it's not a function of voltage, strictly speaking, but it's a function of how much energy is being injected into your circuit. So even though that spike on the front end may look scary, it really is not going to be a problem. We haven't had any issues with that. That's if you're familiar with GDTs, you're familiar with that, because that's a function of what the GDTs do. If you're not familiar with GDTs, rest assured that people have been using these for a long time. It won't be a problem. It probably won't be a problem. You need to go through due diligence in your design work. So let's take a look at some of the advantages. So an IsoMOV embodies a GDT and an MOV in series. And as I mentioned before, that is a magic complement for each other. For example, the problem with the GDT is once it triggers, it crowbars the line, it shorts it out, sucking up all that current, protecting your load, which is what it's supposed to do. But if this is on a power supply, and your can supply enough current while the GDT is triggered, the GDT will just sit there and keep sucking up that current, right? It will never come out of reset. It'll never come out of arc mode and be resetted until that current drops to zero or close to zero, but below 1 amp, for example. Well, with an MOV in series, the MOV, for current to flow, the MOV has to be in this clamp mode, and that takes quite a few volts. Like I showed you in that previous schematic, I showed 300 volts. So if your supply is below 300 volts, the MOV is not going to clamp. The MOV is not going to allow any current to flow. So the surge comes, 2 kV, everything triggers, the surge goes away, your voltage drops back to its normal level, which is below the MOV clamp level. The MOV turns off, which in turn starves the current on the GDT, so it will now reset and go back to its normal mode. That's called GDT holdover, the idea that the GDT stays on even though the surge has gone away. So the MOV solves the GDT holdover problem. And as I said before, the GDT solves the leakage problem with MOVs, right? A GDT is a gap. There's no leakage. And so each one overcomes the deficiencies of the other. Now, number two, not only have we put a GDT inside the MOV, but we've optimized the current density through the MOV. If you look at the forensics of MOVs that fail So I use the word fail. That's unfair. It's really end of life. These things do have a finite lifetime. GDTs and MOVs both have finite lifetimes. But when you look at how they enter this end of life, you'll see there's pinholes at that metallization contact. What's going on there is that there's current crowding. These materials are not perfect. The current densities is not equally spread out over the entire surface of the disk. It crowds in one area, so that part gets really hot, and that's where the pinhole occurs, that's where the failure occurs, and that's where the flame out occurs. We've been able to optimize that interface to spread out that current density so it more equally spreads out, flows out over the whole disk. So there are no pinholes, there are no hot spots. So the lifetime is very much improved. Not only the lifetime, but for the same disk size, we can allow more current to flow. So you'll see these parts, for the same size, have higher current ratings. Number 3, higher voltage, extended temperature range, 125 degrees. C is hard to find for components like this. These will work up to that higher temperature. These are recognized as a UL 1449 Type 4 component. Lifetime is interesting because there's no leakage. Normally, this MOV is not aging. It's not sitting there aging, just even with no surges like a normal MOV would. This thing will only age during the surges, during these transients. So the lifetime is much longer than you'd find in a normal MOV. Temporary overvoltage is a common hazard for AC lines, right? You've got a compressor turns on or off, or some motor, and the voltage swells up to a higher voltage than normal for a short time, but it could be hundreds of milliseconds or even longer, long enough to cause some problems. So how does this stack up against temporary overvoltage? I have a movie here which will show you how these various flavors of MOVs fail. First, you see the red one there, that's a thermally protected MOV. The middle one is a normal MOV, and you can actually see we've captured the frame where the little glow is coming up from the inside, right? That thing just is gonna, you'll see what it does. And on the right-hand side is the IsoMOV. Now you can't see it, but across the top are some poor man bare wire fuses that will allow us to protect the AC line, right? We've got this on a variac, and so we bump the variac up, it's an AC line, and we don't want to really blow anything up equipment-wise, so we put these fuses in there. MOVs typically fail short, so they'll blow the fuse. So with the fuse, we can see if something happened or not. And I already show you what you're gonna see here. First, the thermally protected. It does not blow the fuse because it has that thermal fuse built into it, which does blow. It protects the MOV, which is what it's supposed to do. The second one blows the fuse, and it blows up. The third one never did blow. We cranked that variac as high as we could, and it never did blow. So it's just sitting there, very nice, protecting. Our experience shows that it will blow around 320 volts AC. So let's take a look at that movie.
What's next? 215.
Mm-hmm. Boy, it's swelling out. Air went.
Okay.
Disconnected.
Yep. Didn't blow the fuse though.
Mm-hmm.
We can see the fuse plainly. Our MOV's getting hot.
Oh, it is. Look at it.
Ooh, that was good. Okay. Now that's 215. Now I'm just going to go up to 260. about 280. Because the other two are already gone.
Yeah. Okay. I thought it blew at 300.
So I hope you saw the red MOV kind of bubbling up and kind of expanding, and then it stops expanding or something happened. That's when the thermal fuse blew. And in the middle MOV, it kind of bubbled up a little bit. Something was going on, and then bam, it violently exploded, which is why people don't like to use MOVs. Now, I keep talking bad about MOVs, but they're certainly better than nothing. And if you need to protect your device and you don't want to spend any money, the MOV is probably the first place to go. They're relatively inexpensive, and they do provide protection. And like I said, most of them by far don't have a problem with this kind of end-of-life phenomena, but some do. If you can't tolerate flaming, then a standard MOV is not what you were looking for. So now I'm going to show another movie with the 3 components, and this is we're surging it this time, right? The other movie was temporary overvoltage. I increased the AC line. This is with a 120 volt line, and we've superimposed surges on top of it. First, I'm going to show a normal MOV. You surge it at 3 Ka, and you keep surging it. And finally, on the 11th hit, and you'll see it flame out. Quite impressive. On the middle one, we took the thermally activated fuse, and again, we surged it at 3 Ka. We surged it, and finally on the 8th hit, it blows. But it blew our fuse. It blew our inline fuse, which says the thermal fuse did not activate, which is somewhat of a surprise. And I'll get back to this after the movie. And then third one, you'll see well, first of all, we couldn't get it to blow at 3 Ka. We had to bump it up to 5 Ka. And on the 17th hit, it finally did. You'll see a little, not nearly as impressive as the other two, just a little pinhole thing. Yeah. I use the word pinhole. I'll discuss that in a minute, because I said they don't do pinholes. But we'll discuss that in a second. So let me show this movie. So I apologize for the aspect ratio. I wasn't expecting that. So what you saw, I hope, is that first normal MOV exploding, but that thermally activated fuse might be kind of a surprise. That thing just disintegrated. If you're using these, you bought these to offer you protection, right? These are not inexpensive devices. These have a complicated structure to them, and that thermal fuse did not offer the protection you thought it would. So what's going on there is these types of devices are good for passing UL, and the way UL tests this is to put the device in line, right, with 120 hertz, 120 volts, AC, make sure it works, take it offline, surges, goes through that surge process, puts it back online to see if it passes, and sure enough, it would pass. This test that we're doing is a more realistic test. We surge it while it's active on that AC line at the same time, which is not what UL does. And for this particular case, you'll see that the thermal fuse did not activate. The device did not get hot enough over a long enough period of time to melt that fusing element. It has the same problem that a normal MOV does. It's just blue. And on the IsoMOV, the last one, you saw that little, maybe you saw a little pinhole on the left-hand side. So if you would open that up, you'll see that the failure mode was not a pinhole type of a failure mode. What's going on here is the epoxy packaging, the coating on it, that was the weak area on the coating, and that was a little crack happened on that left-hand side to allow the gases to escape. So that's why it looked like there's still a pinhole there, but it's an epoxy packaging issue. It's not a failure of the current crowding and current densities. I'm going to see if I can play this again so you can take a look at it one more time, just so you can see, after my discussion here, you can kind of see what's going on. That little pinhole there. Okay. All right. So if you look at the data sheets on an IsoMOV, you'll see the numbering system, the ISO-M3. The 3 stands for 3 Ka or 5 Ka or the 8 Ka, multiple hit type of limit. You'll see the voltages there, up to 700 something volts. These are on the higher end of the voltage scale. And you'll see the one hit, 10 Ka, 15 Ka. These are pretty nice devices, actually. You won't find anything like this in the size in the market. And because they're so good, you have a couple options now. Let's look at the 14 millimeter. Well, let's look at the rows, best-in-class MOVs. Right now, in 10 millimeters, you can find 2 Ka parts, 3 Ka for 14 millimeter, 5 Ka for 20 millimeter. But the IsoMOVs bump this up. So, like for a 14 millimeter part, you can keep the same part, swap out your MOV with an IsoMOV, and you've almost doubled your capacity, around 50% increase from 3 Ka up to 5 Ka without changing anything. Or you can move from a 14 millimeter normal MOV down to a 10 millimeter IsoMOV, give you the same protection, but now you're in a smaller package, so now you're saving some space. These, like I said, so MOVs have been around a long time. There's not much investment in these, and so when something new comes out, it's got to be fairly special, and that's what these are. These are nice parts. If you don't like MOVs, you would like these. Let's look at some of the benefits. There's a bunch of check boxes here. Are they small? Low leakage. I talked about a lot of these, lower clamping voltage. Does it have the GDT to extend the life? Overvoltage tolerance, et cetera, et cetera. And MOV, it doesn't really check any of the boxes. It's like I said before, it's better than nothing. It's kind of your first gateway into a protection product. The thermally protected MOV is UL certified, but it's still an MOV, so it still has some of these other issues. The GDT does not extend its life. It does not have state-of-the-art surge ratings. It's not high temperature. So the GMOV is Bourns' first hybrid product. It took our flat GDT and an MOV and sandwiched them together into a common, and encoded into a common package. So it's a discrete GDT and a discrete MOV put together into a common package. Again, it's pin compatible. It's a nice part, but doesn't have the integrated solution that the IsoMOV has. So it doesn't benefit from the optimized current densities, for example. So it checks off quite a few of the boxes, similar to if you had a discrete GDT and a discrete MOV in series. These would have the same kind of advantages. But the IsoMOV provides much more, high temperature, pretty nice part. Yeah. So because these hybrid protectors are new, not all the standards bodies really have recognized them yet. You won't find them in there. UL 1449 edition 4 does recognize it as a type 4 component, but some of these other standards don't know what to do with these yet, but they know they need to. So they are currently in the process of writing standards around it, and it looks like it'll occur under IEC 37B, which is currently being written. So where can you use these things? Well, here's some examples. I showed power supplies and smart meters and appliances and SPD, surge protection, those devices, those, the gray boxes on the side of your house. You open those up, and what's in there? Well, these kinds of things aren't in there. Basically, solar panels are outside. They're exposed to lightning hits that are nearby. And basically, anything that's plugged into power could use protection, and IsoMOV is ideal for that kind of protection. So I've got a QR code there. I should have warned you about this. Quick, take a picture if you wish. That'll take you to our web page where there's lots of publications, and I show them here. There's links available as well to help you design these in, what kind of characteristics you need to look for. You're right, these are nice devices, but they still take design work. And these papers will help guide you into how to implement these in a very cost-effective way. So that brings us to the end to our presentation. Thank you very much. And now it is time for questions.
All right, since a few of you have already submitted questions, we're going to jump right in. If you'd like to submit one now, type your question into the Ask a Question box and hit the Send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. Okay, so the first question we have here is, will you have a higher voltage IsoMOV?
Thomas, would you like to take that one?
Yes. The high voltage IsoMOV is on our roadmap that we will make them, but currently we have a very small request on the high voltage, so we focus on these particular voltage currently, but yes, it will be on our roadmap.
All right, so the next question we have here is, what is the tolerance range of the GDT trigger value, and does this value change with the number of operations?
Typically, when you first do the search, the trigger value is higher, but as it ionized in the gas tube, where you know about the gas GDT technology, the trigger will be low and lower every sequential search. But if the unit been sitting idle for a long time, it basically almost like reset to the beginner again. So the initial, what we call the VFP, maybe seem high, but like Paul explained that in his presentation, that hardly have any energy on there. So it's pretty much similar to an ESD event.
So the tolerance is, aren't they like 20% or so if you buy a virgin new part? There's a spec in the data sheet, isn't it like a 20% tolerance?
Yes, GDT typically is 20%, and MOVs have 10%.
Okay.
So they combine somewhere around 20 to 25%. But the
right.
but the MOV clamping part, will basically stay the same within the 10% like the standard MOV.
Okay, so the next question we have here is about the failure mode of the IsoMOV, and it goes, is it supposed / predicted to be like how it happened in the video, and will the IsoMOV be open or short-circuited?
Well, the
Right.
failure mode is basically typically on the surge current, depending on how much, if it exceed or if it below. But the way that we design is we basically eliminate this kind of pinhole failure. Paul, you want to add something to that?
Yeah. So the IsoMOV can be thought of as having a GDT component and an MOV component. And typically, it is the MOV component that will reach its end of life before the GDT does. And typically, the MOVs will fail short, which means the GDT is still in the circuit. And that's another advantage they didn't talk about. When the MOV the MOV portion does reach its end of life, the GDT is still there to still offer protection for your circuit. But like Thomas said, it depends on the how big that surge current is. I mean, if it's big enough, it's going to vaporize the whole thing, right? So then it's an open circuit. But if you stay within its specs, then yeah, it'll typically fail. The MOV portion will fail short. And the question was, is it typically what you see here? No. It took us quite a few tries to get this. Usually it's not impressive at all. It's just it shorts out and the GDT's left, but there's nothing to look at. And so I wouldn't say that this is the worst case either, because again, it depends on how big that surge current is. But usually, if there's a certain percentage of MOVs that will fail catastrophically, the percentage of these will be much, much less. We don't have enough statistics to really know.
All right, so we have another question here that is, can the IsoMOV clamp surge voltages at lower voltages such as 400 volts?
Well, to answer that question, it really depends on what is your operating voltage. So that, so the design, and also as with the MOV, the higher surge current will result into a higher surge voltage, higher clamping voltage. But if you do have an application that requires to go that low, you can talk to one of our FAE and we can take a look at it and maybe help you find the right solution for you.
So I don't know if you can see it, but I moved the slides to the datasheet numbers, and those voltages dropped down to 200-something volts DC. The question was, will it clamp down to 400 volts? And the answer is yes.
Well, it depends on the operating voltage too.
Right, exactly. It's got to be above your operating voltage, and then you get what the clamping voltage is what you get. And that's what's hard, right? You want the operating voltage high and the clamping voltage low, and the closer those two get, the harder and harder it is to make devices.
And actually, it's going to bring up a good point. If you contact us afterward or one of our FAE, we actually have a white paper kind of showing how to select the MOV, and from that white paper, you can actually apply the same thing for the IsoMOV.
All right, so we have another question here that asks, with the introduction of the IsoMOV, will your GMOV go away?
I'll take that one.
Okay.
So as you saw, the IsoMOVs go down to 200-something volts. And as I alluded to, so MOVs have current limits and voltage limits. And the current limit is due to current density, right? So the bigger devices can handle more current, so the size, the diameter of the disk. But the voltage limit is based on the thickness, right? So there's an electric field in there. So the thicker devices can withstand more voltage. So for low voltages, the devices get thin. And an IsoMOV has 2 disks. Each one is half the thickness of a normal MOV. So for low voltages, those things get really thin, and they get really brittle, and we basically can't make the device. So a GMOV doesn't have that problem because it still has a normal MOV disk. So for low voltages, GMOV is the only hybrid solution that we would have. IsoMOVs will not get down that low in voltage. So yes, GMOVs will still stick around, if nothing else, just to give us solutions for low voltage applications.
Okay, so the next question we have is the GET available for a selectable range of trigger values?
The GET, since the IsoMOV, so IsoMOV was designed to match the GDT value to the MOV. So no, you don't have a way to select a certain value of the GDT portion of the design.
Okay, so the next question we have is, when the MOV fails short, what makes the GDT turn off?
On this particular one, where we found that when the if the MOV portion fell short, it still have enough impedance in it where it help the GDT still extinguish. But when it gets to the point where the GDT no longer be able to extinguish, basically you will short out that line completely, and that will take out the fuse. And we done this testing on with a 10M fuse, with a typical of standard testing.
All right. So
right. You still need an external. You still need an external circuit to extinguish the GDT, and a fuse is one way to do that.
Okay, so the next question we have here, it seems to be a two-parter with an introduction. It goes, normally MOVs will use several pieces parallel together. On slide 16, the same dimension of the MOV and IsoMOV, it looks like the IsoMOV will have a higher surge rating. Can I use a single IsoMOV to replace 2 or more MOVs in the same space? And the second part of that question is also, IsoMOV, can it have a longer lifespan as well compared to several MOVs?
So if you look at Paul, one of the slides show that the IsoMOV actually have the same size MOV, but have a rating of the next side higher. You know, for example, if you look at the 14 millimeter MOV, that one typically have about 3 Ka rating, but the IsoMOV on the same side have about 5 Ka. So it almost equivalent to if you put 2 MOV in parallel to get the same rating of IsoMOV.
Right. When you put MOVs in parallel, they don't add up directly, right? You're going to get some current hogging because these are not precision devices. And we typically use a 40-60 split between 2 MOVs. And as you add more and more MOVs, you can do statistics and get some kind of a bell curve thing. But yes, you do get increased current capability by putting more MOVs in parallel. You can do the same thing with IsoMOVs. You can put them in parallel as well, because the clamping part of it is due to the MOV part of it. And the lifetime is improved because the IsoMOVs only age during transients, not all the time like a normal MOV would. I hope that answers the question.
All right, so another question we have is, what is the waveform for slower rise time events? The example showed a very fast impulse, but overvoltage can be slower. Energy will be let through until the GDT fires.
On that question, what is the waveform? Yeah, a slow rise time event. You mean like if it's in like an AC rise time, thing like that? So typically on some of these examples where we actually test based on the 8x20 surge waveform, and if it's a slow rise time, again, the GDT, the IsoMOV, basically have what we call the VFP. So at the higher surge, higher rise time, that actually, because the GDT is a lot slower to respond, so you will see a higher peak breakdown compared to if you do slower, and the slower rise time will actually have a lower breakdown than the high rate of rise.
Yeah, let me say it this way. GDTs take time for that gas to ignite. So if the surge is coming in fast and the rise time is very quick, it'll sneak past before the GDT has had time to ignite and clamp it down. So you're exposed to that fast initial spike. But for slow rise times, the GDT does have time to ignite and catch that. So that spark over voltage, the voltage at which the GDT triggers, changes with the rise time. And this is in the data sheet. And they can go down to less than 100 volts or so, depending upon which part you pick. So for slow rates of rise, the GDT will be able to keep up, and that front end spike will drop. It'll still trigger.
All right, so this next question asks if you can elaborate on the lifetime and aging during transients. How many transients or surge cycles can it withstand?
On the how many transient cycle, basically we follow the UL testing method, which they have 15 operation of what we call the I nominal, and basically that 15 operation represent the life of the surge transient on those particular components. So if you look at the MOV, the PTVS, something like that follow the UL, basically that 15 operation of the normal current is what considered as a life of that component. We do have customers that may want to say, okay, we want to search at lower than the I nominal. How many can it take? So some of those is really depend on how long do you allow to rest between surge and et cetera, et cetera. So those are a little bit harder to give you a definite answer. But if you work with us, we will be able to define that for you.
All right, so the next question is, how would you approach using an IsoMOV to pass the varistor overload test in 62368-1, where a fire enclosure is not a possible solution? We would usually use a thermally protected MOV for zero risk of flame as per requirement of the test.
Okay, on the IEC 62368, and there is an exemption if you take the MOV and you double the voltage, meaning if you do 120, you put in a much higher MOV, then you have that passing requirement of the temporary overvoltage. So in this instant, basically on the IsoMOV, because that typical trigger voltage or breakdown voltage typically is also at higher than twice of that clamping voltage. So the 350 volt, for example, component, your typical breakdown around 700, 750 volt or so. So that's how, the test was being done.
All right, so another question we have here is, if the surge is only 1.2 kilovolts, there will be no protection at all since the GDT will not trigger, right?
Again, depend on the component that you select. So I think on the data sheet we do specify what is the breakdown voltage of that component. So yeah, if you pick the one that have a very high breakdown voltage, then it probably will still let through the 1.2 kV. So again, it's one of those where you have to know which is the right component to select and put in. And, we can help with that as well if you contact one of our FAE or sales.
Okay, so we have another question here, but before I ask it, I'll note that there have been some requests to put the QR code for the website back on the presentation so people can snap a picture of that. And but the question we have here is, can you lower the clamping voltage by putting multiple IsoMOVs in parallel?
Yes, you can, but there's always a rule of thumb that I use is because you don't really actually double when you put two in parallel. For example, if you take a 3KA and a 3KA, you put them in parallel. Typically you say should be handle 6KA, but because they are not matching even with the MOV, unless you match it really well, but even that, you still have one that will clamp before the other. So the first one, to be on the safe side, this first one we always say that it will probably take 60% of the surge, and then the remaining 40 will be on the second unit. So if you put them in parallel, yes, you can increase the surge rating, but keep in mind that that's not really double.
Right. The question was about, can the clamping voltage be made lower? And the answer is no.
Yes.
You put
the clamping voltage. The clamping voltage does get lower because now you have more surge, more surface area on the 2 unit instead of 1 unit. And again, that I would point that to the white paper on selecting the MOV, and that white paper kind of describe on if you put 2 in parallel, what you're expecting to see as for the clamping voltage.
Okay, Thomas, you and I'll have to talk about that offline.
Yeah. Yes.
Okay.
Sorry.
Okay, so we have another question here about placing IsoMOVs in parallel. Can you put multiple components in parallel to increase the surge rating?
Yeah, that one I just answered previously. So
right.
Maybe I got
yeah.
that mixed up, yes.
Okay, so another question that just came in was, how does the breakdown voltage change with temperature?
Because this particular design, the IsoMOV, you have the MOV and the GDT kind of isolated. So if you're working within the operating temperature, I think on the IsoMOV is up to 125 Celsius, and typically you don't have a whole lot of change on that one. On the operator on the breakdown. So they pretty much stay within the tolerant range.
Okay, so another question that came in is, the IsoMOV spec table that you showed didn't include max energy measured in joules, which commonly pops up in MOV data sheets. Is there a reason for that?
typically we didn't consider that on there, but there was no reason that we didn't put it on. We just didn't really. A lot of customer doesn't really ask about the joule rating. They're more asking about the I nominal, which is basically what the UL spec for any kind of SPC or SPD device. So we just focus on that.
All right, so another question we have here is, what is the voltage swell/TOV overshoot allowed? I think the questioner wants it in terms of percentage compared with the MCOV value of corresponding IsoMOV.
If I'm mistaken, to be a Type 4 component, you have to have about 20% or 20 or 25. Don't quote me on it. I don't remember off of my head, but around 20 to 25% above the MCOV.
All right, well, we do have a few more minutes, so maybe we'll wait just a few seconds to see if any final questions come into the queue. And so we have another one that just came in, which is both the GMOV and the IsoMOV are through-hole components. What about surface-mounted hybrid devices?
The service mount is also on our roadmap currently, and again, as more and more customer requests on it, we will put that more on the priority of roadmap. But currently, very little of any asking about the service mount, so we kind of have that on our roadmap, but really not moving up yet.
All right, once again, we'll just wait a few seconds to see if any final questions come into the queue before we wrap up the call. And so we have another one here, which is, can this be ATEC/A2 approved?
That one, I don't believe we are AEC-Q approved for the IsoMOV yet. So I'm not quite sure if we, continue doing that. But I think if I have to talk to the product line to make sure that we have that on our roadmap or not. So we still working on that currently.
Actually, I believe the question asked if it was ATEC approved.
Oh, ATC. Oh, okay. ATCE. I don't know that. Paul, do you know?
No, I'm not familiar with that. We'd have to look that up.
Yeah, I'm not familiar with that.
And so that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Bourns for sponsoring today's event, and of course, all of you for joining. Have a great rest of the day.
Thank you.